In this video, I'm going to talk about moment of inertia and Newton's second law. This is part of option B from the old syllabus ending November 2024 and part of Theme A.4 of the new syllabus starting May 2025. That means for the old syllabus, it's relevant for HL and SL, and for the new syllabus, it's only relevant for HL students. Please take a moment and read the success criteria I plan to cover in this video. Now earlier, in translational motion or just linear motion, if I have an object here, all I'm interested in really is its mass. But as soon as it starts to spin, and I've got examples here of figure skaters, a very common example, then it's not just the mass of the figure skater that's important. We also need to know about how the mass is distributed. So you've probably seen plenty of times where they start spinning on one foot like this and then start to pull in their arms tight. Or perhaps this one, where they stretch up straight. So instead of the mass being very far from their axis of rotation, it becomes closer. Shut your eyes and think, what does it end up doing? Yeah, they end up spinning faster. We'll do that in another video later. In the old data booklet, here it is here, moment of inertia. Here it is here for the new syllabus. So how are we going to calculate this? Well, there's something about the mass and also how far it is from that axis of rotation. And if we want to calculate the moment of inertia, we're going to take each point mass in my object, multiply it by the radius squared. So in other words, the farther it is, the greater the moment of inertia. I'm going to do that for every single point. So let's look at this. What if I choose right here and I say that my object here, these little dumbbells, we're going to assume that this line in the middle has no mass at all. And I'm going to rotate it in a circle about this point. That means my moment of inertia is going to be just mr squared. This is m for mass, this is r as a distance, and this is m for mass. So this part has no moment of inertia because there is no radius, but this one being rotated does have a radius of r squared. But what if I now choose this point as my place for rotation? Now I have this mass being a distance of 1/2 r, and this one is out by a distance of 1/2 r. So now, if I rotate around B, I'm going to have my mass is m, and the radius will be, it's a distance of r over 2 all squared. And I have my second one. So you notice that if I rotated around this point, my moment of inertia was mr squared. But if I rotate it about this point, now my mass is distributed differently. I have a different moment of inertia. Now, if I have an object in 3 dimensions, I really am not going to be able to do it for every single point. And yes, that's going to involve calculus. Now you can see here, somebody else has done it for me. I have all of these different possibilities. Notice here for a hoop, this is when I'm spinning it with my axes in the center. But if I have my axes vertically and now it rotates in this direction, I have a different moment of inertia, kind of like in my previous example. Now these aren't in our data booklet, and what does that mean? It means that if we need to know one of these special shapes that have a pre-calculated moment of inertia, they're going to have to give it to us. They're not going to expect us to memorize all of these, but I do think it's important for us to recognize that there is a formula for some of these shapes. So, moment of inertia, all about mass and being distributed. Well, let's think about some of the equations we've had before, because just because we're rounding doesn't mean we're going to throw out things like Newton's laws and momentum or anything like that. So let's just look at Newton's second law for the moment. Here we got force equals ma. Well, in rotational motion, I'm not interested in the force, I'm interested in the torque. And the old syllabus would write it like this. And instead of mass, I now have moment of inertia. And acceleration, I now have angular acceleration. Okay, so let's do an example. Example 1. Which of the following factors does not affect the moment of inertia of a spinning body? Now, if you remember the examples I gave you, we did this one here, and we actually calculated the moment of inertia. The distribution mass is definitely going to affect the moment of inertia. But remember, we're looking for not. The orientation of the axes, the direction in which it's spinning. I said, for one, what if it's spinning around this point or here? And I got two different moments of inertia. So this will definitely affect it. The mass that I would use, well, mass comes up in every single one of them. And if the distribution of mass is important, so is mass. But how fast is it spinning? No, that doesn't matter. So the answer is D. Here's example 2. We've got this little toy that we'd have in a playground. Some people call it a roundabout. And I'm going to say that this one is 2.6 meters in diameter. And I can't calculate for all these points, so somebody has already done it for me. It's 250 kilogram meter squared. And this is going to be initially at rest. Now, if I apply a force here on the bar, and that produces a torque of 30 newtons, let's do some calculations. In part A, we say the child pushes with the force for half of a revolution. Now, what's going to happen if I apply a force on here for a certain distance? It's going to go from not moving to moving. It's going to speed up. Now, if I was doing linear motion, I would say, oh, it's accelerating, so use suvat. But we're not doing linear motion, we're doing rotational motion. So instead of S, I have theta. Instead of U, I have omega I. And I have omega F, initial and final. I have alpha, and I still have T. So let's just get rid of these. Now, if it goes around a half revolution, that means theta will equal pi. One full revolution is 2 pi. It starts from rest, so this will be 0. I'm looking for the speed after one revolution. Do I have any information about how long it takes? No. Do I have any information that I could do to solve alpha? Well, I don't know it yet. Let's go back to Newton's second law. Torque is going to be moment of inertia times angular acceleration, which will be my 30 over 250. That's going to give me 0.12, and this will be radians per second squared. So I need my suvat equation, rotational style, that has S, U, V, and A. Well, normally I would say that's V squared equals U squared plus 2AS. In this case, so let's do some substituting. This is 0. So my omega F is going to be root 2 times my alpha, 0.12, times theta, which was pi. And if I pick up my calculator, I get 0.87 rads per second. I'm just going to put that data up here so I can erase this and I can have some more space. Okay, part B. At this point, another child runs with a mass of 40 kilograms, jumps on the roundabout at 1.1 meters from the center. What is the new moment of inertia? Well, remember, moment of inertia was going to be the sum of mr squared. Now, I've got the 250 for the roundabout itself. So now I'm going to treat the child like it's a point mass. as in all of its mass is centered at this one spot that's 1.1 meters from the center. So I'm going to say 40 times 1.1 squared, and I'm going to add them together. It gives me 298.4 kilogram meter squared. And C. What is the new angular acceleration? Well, in this case, we're going to have to assume that the torque remained constant. And I'm going to use Newton's second law again. So tau equals moment of inertia times angular acceleration, or angular acceleration is going to be my torque, which was 30, my new moment of inertia, 298.4, and this is going to give me 0.10 radians per second squared. Just as a note, this probably should have been rounded to 300 to give the correct number of sig figs, but I left all the data there so that I could use it in the second part. So please take a moment and read the success criteria again. I hope you can say yes to all 3 of these points.